Welcome back. Recovery of natural gas liquids from natural gas is quite common in natural gas processing. Recovery usually done to produce gas without any condensation, and also to meet sales gas specifications and to maximize liquid recovery, as the liquid is more valuable than gas. In this model, we will simulate a complete NGL fractionation plant, consists of 3 columns: dimethaniter, diethaniter, and dipropanider. You can find the case document called NGL fractionation train. And in this case, we have 2 streams coming out from 2 different wells. We have the flow rates, temperatures, pressures, and composition for each one. Let's open a new case. And as we used, we will start with adding components first. Now, let's select the property package. We will use Pink Robinson for this case. And now go to simulation. Let's add the first stream using F11. I'll name it well 1. Now I'll add the composition for this stream as we have in the document. And make sure that the summation is 1, which means that you have entered the composition correctly. I will add the conditions we have. First temperature, -140 Fahrenheit, not Celsius. Pressure 330 psi. And the flow rate, pound/mole per hour. Now the stream is solved and it's fully defined. The same for stream number 2. The summation is 1. For the conditions, temperature -120 Fahrenheit, and the pressure, and the flow rate. Now we will add another stream, which is an energy stream with the duty mentioned in the case, just to increase the efficiency of fractionation inside the dimethaniter column. From here, the red arrow, this is the energy stream. I'll add it here. I'll name it external duty. And the heat that is supplying is 2 million BTU per hour. It's fully defined now. Now I'll add a reboiled absorber as a dimethaniter. When I write reboiled, I find this one, reboiled absorber. Well number 1 is coming from the top, and well number 2 is coming to stage 2, as mentioned in the case. The number of stages are 10. You can change it from here, and you can change it according to the case. The overhead stream is DC1 overhead. Do not forget to name the column. DC1, and the bottom stream, DC1 bottom. The reboiler duty is DC1, reboiler Q. We can see here that you can choose the option to have a reflex stream through a pump. And here also, you can change the numbering system from up going down or from bottom going up. So next, there are 3 options depending on the reboiler configuration you have. If you have a different configuration in your plant, you can change it accordingly. Then next, the top stage pressure, as indicated in the case, and the reboiler pressure. Then next, record the top stage and bottom stage temperatures as we have. We have here the top stage temperature is negative 125, but it's Fahrenheit, and the reboiler temperature is 80 Fahrenheit. Then next, we did not have what is the boiler pressure, so let's press done. A new window for the column configuration will appear, indicating that the column is not yet ready. As you know, any column is being solved using a lot of equations that relate parameters with each other. To know how many variables I need to let HYSYS solve this column, you can go to Monitor to check the degree of freedom. The degree of freedom is 0, which means that the number of activated variables here, just one activated variable. The number of activated variables here are enough to solve the column, which means that one variable is required to solve the column. If you unchecked this variable, you will find that the degree of freedom is 1, which means extra variable is required to solve the column. You can also delete one of these variables and add another one, according to your requirements. We already have the overhead flow rate. So I will activate it, and I will enter the value over here from the case. And now you can find that the column is convergent. Also, if you have any estimate for any other variable, like here, this is activated as an estimates, it could help HYSYS to start with, but will not be considered as an input. You can just check here without checking on active box. Now we have run the column, and now it's convergent. HYSYS now designed the column and solved it. However, it doesn't make sense to make the outlet overhead flow rate that we defined here. It doesn't make sense to make it constant, because the function of the demethanizer is to give outputs with the specifications that I require, which is the composition, not constant rate. Any changes in the feed will result in non-desirable specifications at the outlet, because you have determined the outlet flow rate and not the outlet specifications. So now I have to change that, and I will ask HYSYS to fix the overhead outlet composition, not the flow rate. So I will deactivate this, and I want the outlet methane to be 96%, regardless of the flow rate. Now I'll add specification. I want the composition of the vapor phase on stage number 1, right? So column component fraction, I'll select stage number 1 and change the phase to vapor. Then I'll select the component and I will call it methane percent. Now close this window and add here 96% as we discussed. Then we activate this specification, we run the column, and the column now is converged, but using the right specification. Now please close the column and save your case. Let's save it ngl fractionation. And now let's add a pump that will transfer the liquid to the deethanizer. The inlet to the pump, DC1 button, and we'll call the outlet DC2 feed. And the energy is Q pump. And as mentioned in the case, the outlet temperature from here, I can record it here, is 2790 kilopascal. Now the pump is ready, solved. Now it's time to add the ethanizer, and let's make it in another lecture. Thank you.